Scattering experiment. Rutherford's alpha particles scattering experiment. Rutherford was the first scientist to provide correct description regarding the distribution of positive and negative charges in the atom. The basis of Rutherford's atomic model was the alpha particles scattering experiment. He bombarded a thin gold foil with highly energetic alpha particles and studied the scattering of alpha particles. An alpha particle is a positively charged particle having a mass equal to that of helium particle and positive charge in magnitude equal to twice the charge on an electron. The structure is equal to twice the charge on an electron. This experiment provided a vital information regarding the structure of the atom. The experimental arrangement is shown in figure 5. When a narrow beam of alpha particles falls on a thin gold foil, about 2.1 into 10 power minus 7 meters thick, the alpha particles are scattered in different directions, which are detected with the help of an alpha particle detector. The alpha particles scattered by the thin foil in any direction were allowed to fall on a small screen coated with zinc sulfide. A faint flash or scintillation is produced whenever zinc sulfide coated screen is struck by an alpha particle. By rotating the screen to various directions and count the number of scintillations with the help of a microscope, it was possible to estimate the number of alpha particles deflected through any angle from the original direction. The whole arrangement was enclosed in a vacuum chamber to prevent the scattering of alpha particles from air molecules. Experimental observations. Most of the alpha particles were formed to pass through the gold foil without being deviated from their paths. Some alpha particles were found to be deflected through small angles, and their angular distribution is fixed, theta less than 90 degrees. Few alpha particles were found to be scattered at fairly large angles from their initial path and come back, theta greater than 90 degrees. A very small number of alpha particles, about 1 in 8,000, practically retrace their paths or suffered deflections of nearly 180 degrees. The graph between the total number of alpha particles, n scattered, and the scattering angles, theta, was found to be as shown in the figure. Graph obtained on the assumption that atom has a small, dense, positively charged nucleus. Observation and conclusions. The large number of alpha particles passing through the atom undeviated indicate that most of the portion of the atom hollow inside. It cannot be solid in any case, as proposed in Thomson's atom model, because alpha particles are positively charged. Hence, the scattering of some of the alpha particles through small angles indicates that atom is responsible for scattering and it must have positive charge. Hence, Rutherford concluded that the whole of the positive charge of the atom must be concentrated at one place, which is contrary to Thomson's atom model proposal. It cannot be disturbed uniformly throughout the atomic volume. For deflection through large angles, it is clear that when highly energetic and positively charged alpha particles pass through the atoms of the gold foil, then a few of them experience a strong repulsive force, so as to suffer large angled scattering in spite of high energy. And these alpha particles will be very close to the positive charge of the atom. Rutherford concluded that positive charge in the atom is concentrated in an extremely small space at the center of the atom. The positively charged body of very small size placed at the center of the atom is called as nucleus. It was found that the radius of the nucleus is only a 10,000th part of the radius of the atom. Another conclusion obtained from the alpha particles experiment was regarding the validity of Coulomb's law. According to Rutherford's assumptions, alpha particles passing through the atoms of gold foil experience repulsive force due to nucleus according to Coulomb's law. That is, force exerted on the alpha particles due to nucleus is inversely proportional to the square of the distance of alpha particles from the nucleus. When the alpha particles pass quite away from the nucleus, they experience a small repulsive force, hence suffers a small deviation from their paths. But the particles passing close to the nucleus experience a heavy repulsive force and scatter to large angles. On the basis of Coulomb's law, he also calculated the number n of the particles scattered at different angles. Say theta is such that n is directly proportional to 1 by sine power 4 theta by 2. It confirms that scattering of alpha particles by the nucleus is in accordance with Coulomb's law, and this law is valid for atomic distances also. Rutherford experiment also gives information about the positive charge present in the nuclei of different metals. Rutherford bombarded alpha particles on the foils of various metals and detected the number of alpha particles scattered in a definite direction in the case of each metal. This number is different for different metals. This shows that positive charge present in the nuclei of different metals is different. Higher will be the positive charge in the nucleus, higher will be the repulsive force, and therefore larger will be angle of scattering of alpha particles. Rutherford proved that number of alpha particles scattered within a certain range by a metal is directly proportional to the square of the magnitude of positive charge in the nucleus of that metal. Based on the Chadwick experiment, he concluded that positive charge in the nucleus of a metal is equal to Ze, where E is charge on the electron and Z is a constant for the metal, known as atomic number. Of Rutherford's atomic model, on the basis of alpha particle scattering experiment, Rutherford proposed the following assumptions. 1. An atom may be regarded as a sphere of radius nearly equal to 10 power minus 10 meters, in which the whole of the positive charge and the whole of the mass of the atom is concentrated in a small region at the center of the atom, called as nucleus, whose size is of the order of 10 power minus 14 meters. 2. The nucleus is surrounded by the electrons in the remaining part of the atom. He also assumed by the electrons are revolving around the nucleus in circular orbits of all possible radii. The necessary centripetal force for circular motion of electrons around the nucleus is provided by electrostatic force of attraction between electrons and nucleus. 3. An atom is electrically neutral. The total positive charge on the nucleus is equal to the total negative charge of the electrons in it. Angle of scattering on the basis of nuclear model of atom can be explained in two ways. A. Distance of closest approach, r. B. Impact parameter. A. Distance of closest approach. An alpha particle which moves straight towards the nucleus in head-on direction reaches closest to the nucleus, that is, it moves close up to distance r0 as shown in figure below. As the alpha particle approaches the nucleus, the electrostatic repulsive force due to the nucleus increases and kinetic energy of the alpha particle goes on converting into the electrostatic potential energy. When whole of the kinetic energy is converted into electrostatic potential energy, the alpha particle cannot further move towards the nucleus, but returns back on its initial path. The distance of alpha particles from the nucleus is called as distance of closest approach, which is represented by r0. Let m and v be the mass and velocity of the alpha particle directed towards the center of the nucleus, then Ke equals to K1 equals to 1 by 2 mv square. Because the positive charge on the nucleus is Ze, that is Q1 equals to Ze, and for alpha particles Q2 equals to 2e. Hence, the electrostatic potential energy of the alpha particle is U equals to U2 equals to 1 by 4 pi epsilon naught Ze 2e by r naught. Equation 1. At the point where it is momentarily at rest, then Ke equals to Pe, that is 1 by 2 mv square equals to 1 by 4 pi epsilon naught Ze 2e by r naught. Equation 2. r naught equals to 1 by 4 pi epsilon naught Ze 2e by 1 by 2 mv square. r naught equals to 1 by 4 pi epsilon naught for Ze square by mv square. Equation 3. The above equation shows that the value of r naught depends upon initial kinetic energy of the alpha particle. As the initial kinetic energy of the alpha particle is increased more and more, alpha particle will reach very close to the nucleus. In this condition, the nucleus will be no more a point charge for the alpha particle and Coulomb's law will be not applicable. Moreover, the nuclear force now becomes effective. As a result, alpha particle is attracted into the nucleus and it never returned on its path. Thus, the distance of closest approach of the alpha particles corresponding to the maximum value of kinetic energy for which the particle is not scattered back will be measured of radius of the nucleus. Impact parameter. Non-head-on collision. Suppose the velocity vector of alpha particle is not directed towards the center of the nucleus as shown in figure 10 below. The alpha particle experiences a force of repulsion and it gets scattered at angle theta with the original direction. According to Rutherford expression for B equals to 1 by 4 pi epsilon naught to Ze square by mv square cot theta by 2. Equation 4, where B is known as impact parameter. Definition of impact parameter. It is defined as a perpendicular distance of the velocity vector of the alpha particle from the center of the nucleus when the alpha particle is far away from the atom. From the above expressions, it can be concluded that for large impact parameter, an alpha particle will go undeviated. For a B impact parameter, an alpha particle will suffer larger angle scattering. For example, when B equals to 0, theta equals to 180 degree. The scattering expression given above cannot be tested experimentally because it is not possible to measure B. According to Rutherford's expression for the number n of alpha particle received per unit area on the screen placed at a small distance away from the thin metallic film, n is directly proportional 1 by sine 4 theta by 2. On the basis of Coulomb's law, the above relation has been verified by Geiger and Marsden. Drawbacks of Rutherford's model. Rutherford's model failed to satisfy the classical laws of electrodynamics. According to these laws, a charge while accelerating or decelerating loses energy by radiating electromagnetic radiations. The electron moving around the nucleus constantly experiences centripetal acceleration, and it must lose energy continuously. As a result, electrons in the Rutherford's model were bound to spiral towards the nucleus and fall into it when all of their energy was lost due to radiation. Thus, Rutherford's model could not explain the stability of the atoms. On the basis of Rutherford's model of the atom, it must be able to emit continuous energy spectrum. However, an atom like hydrogen has line spectrum. Thus, Rutherford's model could not explain the spectrum of hydrogen atom.